Computer memory dictates the physical boundaries for how information is stored and accessed. Every data structure is governed by strict rules of traversal, and solving algorithmic problems requires working within those specific mechanical limits. The singly linked list is built on a unidirectional architecture. Once constructed, it locks its connections forward, creating a one-way sequence of independent memory blocks. This diagram shows a standard 5-node linked list. Each block contains its value and a single arrow pointing one step ahead. To remove the second node from the end, we try to go backward, but attempting to trace backward from the tail is physically rejected. This structural limitation creates a conflict. To locate a node based on the tail, you must either use additional memory to store the nodes you've already seen, or use additional time to traverse the list multiple times. Calculating relative positioning is only simple when the total length of the dataset is known. In a singly linked list, that total length remains hidden until the pointer actually reaches the end. We measure our solution's efficiency using two metrics: time complexity, the number of operations required, and space complexity, the extra memory consumed during the process. A basic brute force approach operates with O of n time and O of n space. It processes each node once, but it also creates a copy of the entire list's structure in memory. Our target zone is O of n time and O of 1 space. We want to execute this deletion in a single pass while keeping extra memory usage constant, regardless of how long the list becomes. To reach this level of efficiency, the algorithm cannot rely on storing a history of the nodes. It must use spatial mapping to find the target in real time. The most intuitive way to bypass the lack of indices is to simply create them. We can convert the linked list into an array to enable direct memory lookups. As our pointer traces the sequence, we allocate a secondary data structure. We copy the memory address of every node into a contiguous array, mapping the entire list step by step. Once the array is populated, the length is known. Subtracting our offset of 2 from the total length of 5 points us to array index 3. With the node immediately preceding our target located, the deletion is mechanical. We take that node's next pointer and route it over the target to seal the sequence. This solves the problem in O of n time, but mirroring every reference into an array consumes O of n space. Using massive auxiliary structures for navigation negates the memory efficiency that makes linked lists a useful data structure in the first place. Recursion is often proposed as a way to avoid explicit array allocation while still processing the list in reverse. During the forward pass, the operating system pauses the current function at each node and drops a new stack frame into system memory. When the pointer reaches the end, the recursion unwinds. The frames pop off the stack in reverse order, which allows us to tick a counter down from our target n. When the count reaches 0, the function returns the next node in the sequence instead of the current one, effectively bypassing the target. While the code looks clean, the physical reality is identical to the array approach. The system's call stack consumes memory proportional to the number of nodes in the list. Because the space complexity remains O of n, recursion does not actually solve the underlying memory constraint. To reach our O1 space goal, we must eliminate all auxiliary storage and work only with temporary variables. We can use a two-pass iteration. The first pass travels from head to tail purely to measure the length of the dataset. A single integer variable counts each node until the list ends. We then convert the relative backward index into a forward coordinate. A length of 5 minus an offset of 2 tells us the target is at index 3. We reset to the head for a second traversal. The pointer counts forward 3 steps, lands on the anchor node, and updates the references to remove node 4. We have achieved O1 space complexity, as we only stored the length and the pointer positions. However, we have processed every node in the list twice. While technically efficient, this redundancy becomes a bottleneck when processing massive, continuous data streams where every traversal has a performance cost. To optimize further, we have to find the target offset without knowing the total length of the list beforehand. We can achieve this using 2 pointers, left and right, both starting at the head of the list. We advance only the lead pointer first. By moving the right pointer forward n steps, we create a spatial gap that represents our target offset. Once the gap is set, we move both pointers forward at the same speed. This sliding window maintains its width as it travels down the sequence. When the lead pointer falls off the end of the list, the movement stops. Because we maintained that fixed gap, the trailing pointer is now positioned exactly one step before the node we need to remove. By converting a mathematical index into a physical distance, we can locate the node in a single pass while keeping our extra memory usage constant. Modifying a linked list requires an anchor. You must be at the node before the target to change its next reference. This creates a problem when the target is the very first node. If n is equal to the total length of the list, we are being asked to delete the head. In this case, the lead pointer moves to the end immediately. The left pointer sits on the head without an anchor. We fix this by perpending a temporary dummy node, ensuring a valid predecessor exists to remove the first element. This sentinel node acts as a structural failsafe, ensuring the algorithm handles every possible index with the same consistent logic. This spatial logic is reflected directly in the final code. We initialize the dummy, advance the lead pointer to set the gap, and then slide both until the end is reached. We have evolved from memory-heavy arrays and recursive stacks to a solution that requires only 2 passes, and finally to this single-pass spatial approach. The result is a highly efficient operation. The algorithm uses the fixed pointer width to measure and cut the list in one fluid motion. By utilizing the forward-only nature of the list to establish a physical offset, we turn a structural constraint into a tool for precise measurement.